Hey everyone, welcome to Dump the Charge. I just wanted to jump in before this video just to say that while editing this video I found that it was getting a little bit long. So I've decided to split the video into two parts just to make the content a little bit more digestible for you guys. The first part, what I'm going to do is I'm going to talk about shock, what it is, the different types of shock that we might come across in our practice. And the second video is going to cover the different stages of shock that a patient might go through, how to identify them, how to treat them. I do recommend watching this video before part 2 because in part 2 I will build on some concepts that I introduce in this video here. So without further ado, let's get to the video. Hey everyone, welcome to Dump the Charge, where we break down and take a close look at concepts of emergency medicine and make them relevant for paramedics and paramedic students. Today we're going to be talking about shock. It's a stupid joke. If you haven't already checked out my video on the hemodynamics formulas, I'd suggest going back and having a look. I'm going to be relying quite heavily on those formulas today. I'm not going to take a lot of time explaining them. So maybe go and have a look if you want some clarification on a few of those topics. So, shock, what is it? Well, I think it's important to make a quick distinction here. So today we're going to be talking about physiological shock. Just be aware that a lot of people refer to certain acute emotional states to be shock as well. That's definitely not what we're going to be talking about in this video. Those conditions, things like amygdala hijack or PTSD from traumatic events, are quite important things to discuss. They are a separate thing altogether. So, what is it? Physiological shock is a state in which the body is unable to perfuse its organs adequately enough to meet metabolic demand. Great, so we've got a definition, but what does that mean? Well, there's a couple of words in that definition itself that I want to break down and make a bit more clear as well. The first one is metabolic demand. Well, metabolic demand essentially is the energy requirement of the body at any given time. Just to function and to live as a human being, there is a certain amount of energy that's required to do so, and that's our baseline metabolic demand. If a particular organ needs to work harder, so for example, get up and go for a run, and our legs are working really hard and our glutes are working really hard, the demand for energy of that organ goes up, and so our net metabolic demand will go up as well. Now, the body meets this demand for energy with fuel, right? And the fuel that we use is ATP. Now, I'm not going to get stuck into the exact formation of ATP, but it's important to understand that we require glucose and oxygen to create it. And this is called aerobic respiration. Now, it is possible to create ATP without oxygen, this being anaerobic respiration, but the problem with that is that we create a lot less ATP, and also there's some pretty dangerous byproducts, namely lactic acid. All of that will become important a bit later on in this video, but keep that in mind. Okay, so let's talk about perfusion. So perfusion relates to the delivery of blood to organs. Now, perfusion and metabolic demand go hand in hand because oxygen and glucose, which are fundamental building blocks for ATP and are vital for us to meet metabolic demand, are carried in blood. So if we have a reduction in perfusion, we have a reduction in the delivery of oxygen and glucose to our organs, and this leads to bad things. So that helps us clear up that definition a little bit more, right? A physiological shock state is a state in which the body is, for some reason, unable to send enough blood to their organs to provide oxygen and glucose in order to create ATP and meet the metabolic demand at that time. So how does the body ensure that we have adequate perfusion and we're preventing this shock state? Blood pressure, right? So how does blood pressure play into this? So the body works very hard to build pressure within my vasculature in order to push blood with enough velocity that it reaches every single one of my organs in my body, as well as the very tips of my fingers and very tips of my toes, but also up against gravity and into my brain, right? To help perfuse my brain. So blood pressure is tied extremely closely to perfusion, and all of that is tied very closely to metabolic demand. And any disruption of any of these things will result in a shock state. Now, there are different types of shock, and they can be broken down into 3 broad categories. Now, within each category and each type, there are different pathologies and illnesses and pathways towards shock. But at the end of the day, the result is the same. Compromise the blood pressure, which will compromise perfusion and result in a mismatch of metabolic supply and demand. Now, I won't be going in depth into the pathophysiology of all of the conditions that can result in shock in this video. It would be much too extensive, and each one of those pathophysiologies does require a video in its own right, which I will be working on in videos to come. Cool. Now, before we dig into each one of these categories, I want to give you guys this analogy to try and help make my point. So here we have a dam that contains water. Next to the dam is a village that is reliant on the water from the dam to function. And over here we have a pump that is responsible for pulling the water out of the dam and feeding it into the village. Now, the pipe that the pump draws water through only reaches down to this level within the dam. So the water needs to be at least at this level for any water to be pumped up into the village. This is probably an inefficient design. It's probably not how dams work, but this works for my analogy, so we're going to use it, okay? Okay, with that done, let's get into it. Let's go to the board. Let's start out with absolute shock. So an absolute shock results from an actual loss of fluid from our circulation, which then cannot re-enter our circulation. An example of this is hemorrhagic hypovolemia, right? Where we have a rupture of a blood vessel causing a leakage of blood out of our circulation, either externally onto the floor or onto a piece of furniture, or internally, right, into one of our cavities, our abdominal cavity or our pelvic cavity. Either way, the blood is leaving our vasculature with no way for it to be put back into our vasculature. Another example of absolute fluid loss, one that's nowhere near as dramatic, is dehydration. If someone has, an illness such as gastroenteritis, where they've got a lot of diarrhea and they're vomiting quite a bit, or a situation where they have polyuria, where they're urinating too much and they're not drinking enough water, they have a net actual loss of fluid from their system, which will mean a net fluid loss out of their circulation. So what are the repercussions of this? Well, an absolute fluid loss pretty much means that we have a permanent reduction in blood volume. A reduction in blood volume means we have a reduction in venous return, which will then reduce preload. Reducing preload means that we reduce the stretch of our myocardium during relaxation, which means that we compromise contractility. Reducing both of these things will reduce our stroke volume, which will reduce cardiac output and eventually reduce blood pressure. Remember that reducing blood pressure will reduce perfusion, which will then lead to a shock state. So let's go back to the dam. An absolute fluid loss is like a crack forming in the wall of the dam and busting open, allowing the water within the dam to flow out into the valley next to it. That's going to cause the water level to reduce, eventually going below the point in which the pipe is able to bring water up and provide the village with water. This is bad. There's no way for us to grab that water that's flowed out of that crack and put it back in the dam, right? That's lost forever into the valley. So we need to replace that water. The only problem is if we replace the water without patching up that crack, it's going to continue to flow out. So to fix it, we need to patch that crack up and get the water in. The second category of shock we're going to talk about is distributive shock. So distributive shock, as the name suggests, means that there is an abnormal distribution of fluid within our body that is somehow causing an inefficient return of blood to the heart, finally affecting blood pressure. This abnormal distribution can take two forms. The first way I'd like to talk about is a relative fluid loss. Now, we've already spoken about an absolute fluid loss, right? Where we have an actual loss of fluid out of our circulation that is permanent. We cannot put that back into our system. A relative fluid loss is a loss of fluid out of our vasculature, but that fluid can be put back into our blood vessels through normal body control. The reason for this is that fluid loss is a result of an increase in vascular permeability. So what does that mean? Permeability is the ability for fluid to shift across a membrane. So if we increase permeability of our vasculature, we're increasing the ability for fluid to shift from inside the blood vessel through the blood vessel wall into the interstitial space, or the space around the blood vessel. Believe it or not, this is a normal body process. It's a way for us to allow white blood cells to leave our blood vessels and fight off infections and that kind of thing that are outside of our blood vessels. The problem occurs when that process occurs throughout our entire body and we start losing a lot of fluid at every region of our body. If this occurs, it will result in a reduction in blood volume and all of the same physiological processes that occurred when we had an absolute fluid loss. Now, please note that this is different to an internal hemorrhage where we have a leaky blood vessel leaking blood, say, into my pelvic cavity. That blood remains in the pelvic cavity and cannot be put back into circulation. This fluid shift, if we're able to reduce permeability, will be brought back into circulation through the lymphatic vessels and that kind of thing, and eventually our blood volume will increase back to normal. The most common causes for relative fluid loss are anaphylaxis and sepsis, both of which cause a widespread vasodilation, which will then increase vascular permeability and fluid shifts from the blood vessel into the interstitial space. So let's go back to the dam and see if we can make it a bit clearer. So relative fluid loss would be more like if someone forgot to close off these vents that are at the bottom of a dam. I don't know if dams have vents underneath them, but this dam does. So if someone's forgotten to close off these vents, water is going to shift from these vents into the reservoirs that they feed. While this is still within the same system, the actual water level will reduce as those reservoirs fill up. If that water level reduces below the point of where the pipe can reach, we have that issue where it cannot supply water to the village. Now, if someone realizes this and closes those vents off, the water level will remain where it is, and the water within these reservoirs can then be pumped back into the dam, refilling it. The water should return back to its normal level because we haven't actually lost any water in this whole process. The second type of distributive shock is when something causes an uncontrolled profound vasodilation, such as can be seen when we have neurogenic shock secondary to a transected spinal cord. So here we have a situation where we haven't actually lost any fluid out of our blood vessel, but we've increased the size of the compartment, meaning now that the blood vessels are too large for the amount of blood that we have in our body. Two things happen here. Firstly, because we have such a massive vasodilation, we are drastically reducing our peripheral vascular resistance. Now remember that resistance to normal blood flow is vital in in building pressure within our circulatory system. So reducing that resistance, reducing that opposition to flow will mean a drastic reduction in blood pressure. But on top of this, by dilating all our blood vessels, we're actually promoting venous pooling and we're reducing venous return. Reduction in venous return will cause a reduction in preload, which will cause a reduction in contractility. This will reduce stroke volume, cardiac output, and worsen the reduction in blood pressure that we already see from a reduced peripheral vascular resistance. Now, going back to our dam, we haven't actually lost any water here. But I'm going to say someone has discovered that there's gold right next to the dam. And so they've decided to excavate and create a mine. The wall of the mine collapses and becomes a part of the dam. So what happens here is that we have a much larger dam than we had earlier and the same amount of water. That water will then redistribute to fill up the now larger dam, causing the actual water level to reduce below where the pipe is. The last category of shock that I'm going to talk about here, I'm going to term mechanical shock. Now, this is a shock process that occurs more so because there's something disrupting the normal mechanisms of the human body rather than there being a problem with the volume of blood within our system. There are two types of shock that I'd like to talk about within this category. The first one is called obstructive shock. Shock symptoms can arise when there's something that occludes or obstructs blood flow coming back to the heart. Now, why is this? If there's something that prevents blood from returning to the heart, it will reduce preload, which will then reduce stroke volume, cardiac output, and affect blood pressure, right? So what sort of stuff can affect it? Well, one of the biggest examples of this is in the presence of chest trauma causing a tension pneumothorax. A tension pneumothorax is a positive buildup of pressure within our thoracic cavity, which will eventually push on the vena cava and cause it to close up. When the vena cava closes up, blood can't shoot through it and get to the heart. We see something similar in late-stage asthma, where gas trapping has become so severe that it causes the lungs to expand and expand within the thoracic cavity, eventually causing an occlusion of the vena cava, preventing blood to return to the heart. So if we go back to the dam to explain this, in this instance, something, I don't know, a boulder maybe, has fallen on the pipe that the pump uses to extract water. So while the pump is still completely functional and the level of water hasn't changed and still at an appropriate level, the rock on the pipe prevents the pump from drawing water up, and therefore the village will get a reduction in water supply. The last type of shock I want to talk about within mechanical shock is cardiogenic shock. Now, this is a very serious type of shock. This generally occurs when something like an acute coronary syndrome, for example, will progress to the point where scar tissue develops around the heart. Scar tissue can't actually contract efficiently, and it actually doesn't stretch very well either. This loss of efficiency in contractility and stretch means that we have a significant compromise to stroke volume. Compromised stroke volume will result in a compromised cardiac output and blood pressure. On top of this, if this acute coronary syndrome damages our heart's electrical conduction system, we'll often end up with cardiac arrhythmias, namely a bradycardia or a bradyarrhythmia, which is a slow heart rate. If we reduce the heart rate on top of reducing contractility and stretch, we're going to significantly reduce cardiac output, which will then significantly reduce blood pressure. Going back to the dam, this is straight up and down malfunction of the pump. The water level is in the right place. The pipes are actually working fine. The pump, however, is damaged. When the pump's damaged, it doesn't matter how much water we have and how good the pipes are, that water is not getting from the dam to the village, and the village is going to suffer. Okay guys, I'm going to end part 1 there. Thanks for watching. If you enjoyed the video, please give it a like and consider subscribing to the channel for any future videos and for any updates. Otherwise, thanks for watching and I'll see you next time.